There is nothing more frustrating than building a perfectly optimized ML model only to watch it completely fail in the real world. Almost every time, the problem isn't your code, it's your data. The algorithm just determines how the system learns, but the training data determines what it learns. So, if your dataset is imbalanced or biased, your model is doomed from the start. Today, we are going to fix that. We are going deep into the ML data pipeline. I'll show you how real companies acquire data, the math behind sampling and labeling, and the exact techniques you need to balance your datasets before they even touch your model. Let's get to work. This is your data pipeline for ML training before you start ML development. So we'll get raw data, we'll sample, and then we'll label it. We'll split the data as training, validation, and test set, and then we'll check for imbalance and we'll augment training set. I'll show you an example of the entire process, and then I'll dive deep into what are the ways we can get the raw data, what are the different techniques in the sampling, and what are different techniques in labeling, and imbalance, and how to augment the data, and why sampling is important, and why not label the entire raw data. I'll try to answer all your questions. By the end of the video, you'll have the entire complete knowledge of the data pipeline for ML training. Okay, so imagine you have a use case where you are trying to develop a sign language interpreter, and you have to gather the data for the model development. How you will gather the data? So an initial data collection campaign can be initiated for gathering at least 1 million short video clips of people making hand gestures. But the problem is, at this stage, we'll have the data, but the data is not labeled. So we don't know what each video corresponds to. So we have to get it labeled. But labeling 1 million short video clips is very expensive. So what we should do? We should get some sample of it and then get it labeled. Every company has budget, so we cannot exceed the budget. So depending on that, we'll sample. So let's see how sampling works. So let's say we have a budget of sampling. We can sample 50,000 videos using human annotators, but we have 10 million raw videos. So from 10 million raw videos, we have to extract 50,000 videos, which contains the unique videos. So we don't want to use simple random sampling, which has similar probability or same probability of each data point to be picked, because in the 50,000 data points, which we will send to human annotators, if we send duplicates, then it is waste of our money and effort, right? So what we'll do is, we have to cluster it, because clustering doesn't require the samples to be labeled. So if you cluster it, how it works is, clustering algorithms group the similar uh, data points. So we'll use clustering algorithms like k-means, and we'll cluster the our 10 million raw videos. Then we'll have different groups of the videos. But the problem is how you will cluster it, because the clustering algorithm only supports numerical inputs, but we have videos. To convert this into numerical inputs, we'll use a pre-trained vision model, ResNet or MobileNet. ResNet or MobileNet are variants of neural networks. So in PyTorch or TensorFlow, you have this readily available with weights, which you can directly use it, or you can download them in Hugging Face. So we'll pass this 1 million videos through this pre-trained vision model, and then we'll get embeddings. Embeddings are nothing but numerical representations of that video. Okay, so this embedding would be of 512 length or 1024 bit length. So once we pass this embedding to k-means, it will cluster our raw data into different groups. So how the clustering works is, once we have the embedding, let's say this is our 3D space. So if we plot the embeddings, they will uh, get plotted closer depending on how similar they are. If they are similar, they'll get plotted closer. Okay. So our algorithm considers the closer groups as a same category. So we have some, let's say 3-4 groups, and then from these 3-4 groups, now we are not leaving out any rare data points. Our job is to pick samples evenly from these different groups which we have. Okay. So we'll sample evenly from every single cluster. Now we'll have diverse mix of all hand shapes, no rare gesture left behind. Now we have to label it. Now we'll send this 50k diverse samples which we'll have to human annotators. So these human annotators, who will be basically, these annotators are experts in the field. So if your use case is medical use case, then you will have medical field annotators. Depending on your use case, you'll hire the annotators. So those people label our videos. So once we have this labeled videos, now we'll know the ground truth labels, right? So we'll split the data using stratified sampling process. So why stratified sampling is, stratified sampling ensures that exact ratios of labels are maintained across all sets. So if there is an attribute like water, which contributes to 2% of the total labeled data, it will be exactly 2% in the training, validation, and test set. So to maintain that ratio, we'll use stratified sampling. So once the splitting is done, we'll only try to check imbalance in the training set and augment the training set data. We don't touch validation and test set, because we have to test our model which is trained on training set to for the real world, right? So we'll have only real world data in the validation and test set. We don't augment it, or we don't check for any imbalance. So now we'll check for imbalance. So imbalance is like, we'll have a different number of data. For example, let's say in our videos, 1000, we have 1000 video samples of hello and only 100 video samples of Z. So there is a clear imbalance, right? So our model would be heavily biased towards hello, and even if it predicts hello every time, then if we train on this 1100 examples, then it will achieve 90% accuracy, because most of the data it has is hello. But we don't want that. We want it to learn this Z also. So what we have to do is, we have to balance the data set. How we'll balance it? That is using augmentation. So augmentation is nothing but, this is our unaugmented data, right? The original data. From this data, we have got the training set, validation set, and test set. From this training set, where we have less examples of Z, we'll try to rotate or increase some brightness, decrease some brightness, or flip the video, and try to have different copies with some changed properties of the same 100 examples. So we'll have 900 different variants plus the original 100. Then we'll have 1000 new Z examples. So now we'll have equal number of hello and this Z examples, right? So now our model will train on perfectly balanced data. Because the validation and test sets were never augmented, the model's true performance can be evaluated on pure real world data. So now we'll see, we'll dive deep into how, what are the ways we can get raw data, what are the different techniques we have in sampling, why sampling is important, and what are the different labeling techniques, imbalancing, balancing techniques, and what are the different augmentation techniques. Let me explain in detail. How do we get raw data? There are different ways to get raw data, okay? Depending on your use case, um, you can choose any one of this. So the system and logging, behavioral logging, it is like how user interact with the application. Based on that, we'll have some data saved in the form of logs. We can use those logs as a data source for the ML model. And hardware and sensor telemetry, nowadays you have this self-driving cars and everything, right? They have a lot of sensors. From the sensors we get continuous data output. So we can use that data as an input for ML models. And web scraping and crawling, nowadays you might have seen this a lot, because all AI companies are scraping the data online and they're training their ML models. Crowdsourcing and user in the loop. So if there is no way to get data, then we can design system where users explicitly or implicitly provide data, like solving captchas, rating recommendations, etc. You might have seen in Netflix, we can like or dislike a recommendation based on which it will improve the recommendation engine. And data partnerships and licensing. We can purchase the data sets from specialized brokers, okay, like historical financial market data or anonymized health records, which are not directly available to us in the market. Synthetic generation. So we can use physics simulators and generative models to create a near realistic examples or data points for us. If we cannot get, it is impossible to get, or it is very expensive to get the data, then we can get it like this. Example is like, let's say, I read it somewhere where Rolls-Royce tried to make an ML model for its flight engine to determine whenever it requires a maintenance, or if the engine is healthy or not. But they have a lot of healthy engine data, but they do not have the faulty engine data, and they cannot replicate it also, right? Because flight engine is very expensive and replicating it would cost a lot. So what they did is they simulated the engine with the exact properties, how the engine behaves in different scenarios, and they simulated uh, what if the if the engine intakes the volcanic ashes, what if the engine intakes birds, or engine was hit by birds, or what if the engine has some malfunction. They simulated it and they got some data using which they trained their ML model on. So for that, for a similar, if you have a similar use case, you can use synthetic generation. Let's look at a real world example, Tesla auto driving, how they get examples, and how the ML model inside the Tesla would be auto improving. They have an ML model which has a shadow mode, okay? So it silently predicts the next outcome while the user is driving. So what happens if the user input and the ML model predicts the same thing, then it will ignore. But if user inputs to the car is different from what ML model is trying to do, then there is a discrepancy. ML model considers it as an edge case, and it will upload the 10 seconds clip from its sensors to the central server, and the server again retrains the ML model. So the uh, data collection and the feedback loop and self-improving loop they continuously work like this. So this is how it works. So now let's get into sampling. Why is data sampling required? uh, the statistical practice of extracting a smaller representative fraction of data points from a massive population. We Let's look at the previous example of sign language interpretation. We have 10 million data points, right? But we do not have labels. So we had to sample some part of it, like 50K, which fits in our budget. So using that, we made we can make a high quality ML model. So for that, and deep learning is not cheap, right? It requires heavy computation, and if you uh, want to train on 10 million or 1 million data set, then it costs a lot. So acquiring raw data is cheap, but hand labeling it is prohibitively expensive and time consuming. So sampling isolates a manageable, highly diverse subset and to send to human annotators, which ensures the budget is spent only on most informative data. So why is data sampling essential in machine learning? For creating training, validation and test set, like we did in our example, overcoming computational limits, because deep learning is very costly and we can sample a small amount of the original large data set, and effectively we can train, iterate and debug the ML model. Handling infinite data streams. See, in production you have a lot of continuous streams of data, okay? So you can't process the entire data like that. Infinite data no one can process, right? So you can sample that and process the realistic representation of the whole data, so that your ML model is updated and you don't use a lot of computational resources in vain. Correcting class imbalance, like we did, there might be some class which has 99.9% contribution and some class which is very rare and 0.1 contribution. So using sampling we can identify this, and then we can artificially modify the distribution to force learning of rare critical edge cases. Types of data sampling. So whatever you're seeing in the screen, these are probability data sampling, okay? So probability is involved in all this data sampling. There is a non-probability data sampling also, which I'll explain later. So there are 4 types, actually 5 types. The 5th one also I'll explain. Simple random sampling, which is like every data item, irrespective of it is um, abundant, common or rare, has equal amount of getting selected, probability of getting selected. So this has a disadvantage of skipping rare data points completely. Stratified sampling, the population is entirely divided into different subgroups, and then from these subgroups it will sample equally, so that rare groups won't be left out. Weighted sampling, let's say we want to prioritize something, like we want to prioritize a recently obtained data. We can add some weight to that recent data so that it gets more priority in sample picking. Reservoir sampling, if you have continuous flow of data, then you can use reservoir sampling um, to sample a part of it. The best part is, from this infinite stream, the sample which you get once you have at any given point, the sample has an equal opportunity for all the incoming stream. It doesn't matter if it comes first or if it comes after as a 100th item or as a 1000th item. It has an equal opportunity. So let's look into let's deep dive into that. So simple random sampling, similarly, it has an equal opportunity. Disadvantages, like as we discussed, rare categories might not appear at all in the final selection. We'll use it if we feel the data set is relatively balanced and you need a smaller, quick representation of the subset to run a cheap experiment, then we'll use it. But in production, most people won't use it. Stratified sampling, we'll pick samples from each group, equal amount of sampling, so that um, how rare they are always included in the selection. But the disadvantage is, like, it is difficult to apply if we have multi-class groups simultaneously, such as multi-label task. Let's say you want to label news articles, whether they are related to finance, whether they are related to technology. But the problem is, like, a news article can also be related to finance and also be related to technology, right? So they are multi-class. So for those things, stratified sampling is not uh, good and very difficult to apply. We'll always use it to create training, validation, and test set to ensure the class ratios remain consistent across all the sets, like how we did it in the sign language interpretation example. Weighted sampling, like I said, we can allow it allows us to leverage our domain expertise to give higher weights to more recent data or some valuable data or classes. But the disadvantage is, like, when we are adding a weight to some class, okay, we are injecting some bias to our model to that particular class. So if the weights are assigned incorrectly, it will inject severe artificial bias into the dataset. Additionally, extreme weights can cause the model to overfit on a tiny subset of heavy samples while ignoring the rest. We'll use it when we know the data we collected comes from a different distribution compared to the true real world distribution, or when we want to prioritize some subgroup in our dataset. Reservoir sampling, when we have a continuous incoming stream, we will use it. The best part is it ensures every element in the continuous stream has an equal probability of being selected, and the algorithm can be stopped at any point with valid probabilities. But the disadvantage is it treats all historical data exactly the same, meaning it does not naturally prioritize fresh or recent data, uh, which is a bit problematic. Furthermore, because it functions as a simple random sampling over a stream, it is highly likely to miss rare events or minority class in the imbalanced data streams. We'll use it in production environments, like sampling a continuous never-ending stream of tweets or server logs. Let me explain this by taking an example. So let's say we have a room where we have 3 chairs and we have an infinite stream of people coming from the door. So what we wanted to do is, by the time we close the door, whoever comes inside, like, we want them to have an equal probability of sitting in the chair. So what we'll do is, let's say first three people comes, they'll sit on the chairs, and the fourth person comes, and there will be a decision point. Decision point usually would be a random number generator, and this fourth person has 3/4 chance to win a seat and 1/4 chance to not win a seat. 3/4 chance is because there were 3 seats and 4 persons entered through the door. And if this random number generates like 1, 2, or 3, then they'll get a seat, and whichever number it gets, that person will vacate the seat. If the random number generates like 4, then he doesn't get a seat. Depending on that, similarly, as the line gets longer, it gets mathematically harder for new people to win a seat. This perfectly balances the probabilities, ensuring every person ever seen has an equal chance of being in the final sample without needing to store the entire stream. But there is one important sampling method, importance sampling. We don't use this much in standard data prep, but it is heavily used in reinforcement learning and for simulating extremely rare events. The idea is simple. If you can't access the exact data distribution you need, you sample from a similar dataset you do have and apply mathematical weights to compensate for the difference. For example, if you want to find the average height of pro basketball players but can only measure people at a local mall, you would heavily weight the data of anyone over 6 feet tall to mathematically pull your results closer to reality. In reinforcement learning, models use this exact trick to heavily amplify the learn from their past failures. Yeah. So I told you, right, there is another concept called non-probability sampling. Till now we have um, had a look at probability sampling. Non-probability sampling, I don't think anyone would ever use, because the selection of data is not based on any probability criteria. There are four techniques we have. Convenience sampling. Samples are selected based on availability. Whatever samples they have, they'll just take it. They don't have a diverse sample set. Snowball sampling. Future samplings are selected based on existing samples. Let's say you want to scrape the tweets in the Twitter X. So you start with sampling few people's tweets, and then you scrape the person's followers and go on, right? So initially you start at some point, and then you scale the sampling to the things which are related to this person. So that is how snowball sampling works. Judgment sampling. Expert decide which samples to include. So this might have lot of bias in before we even start model development. Quota sampling. Samples are selected based on quotas for specific data slices without randomization. Let's say we want there is a survey where we want to take some details uh, of different groups, below 30, 30 to 60, or above 60. So even if we want to collect 10 data points for each group, even if we have 50 data points of this 30, we'll only take 10 data points, and we'll try to get 10 data points for the other groups, right? Because of the quota. So these things were not used in any of the production systems. You can ignore, but just to have knowledge that this thing exists, I'm saying it. Labeling techniques. So hand labeling, like we used this for in our example of sign language interpretation. So once you have the data, you can share it to human annotators to manually tag data, but it has high accuracy because the accuracy would be exactly human intelligence, right? But the problem is it is very expensive, very slow, and humans has to humans have to look at the data. So they are it poses threat to data privacy, suffers from label multiplicity because humans disagree sometimes, and we'll use it when we want highly accurate labels. um, Mandatory for creating final validation and test sets. You must always evaluate your model's true performance against perfect human labels. It is also required for highly complex or nuanced tasks, such as like medical scans, etc. There are other labeling techniques also, like natural labeling. Like this is like, for example, you have some recommendations, and a user click on the recommendation, then the system takes it as like the human like the recommendation system is working fine. So that is how it interprets from the user actions. This is called natural label. And weak supervision. uh, Weak supervision is like a is done via programming. It utilizes labeling functions like regular expressions or database lookups to programmatically generate labels, but it has some noise. But the best part is it can be scaled infinitely. You can reuse them, and it doesn't have to care about the data privacy and everything, because it is a machine which looks at them, not a human. So it is good, but the problem is they are less accurate and more noisy compared to human generated labels. Um, but the good part is I read somewhere which says if you can actually uh, clearly convert the domain expertise, then this gives comparable performance to the human labeling. Okay. Active learning. Let's say we don't have good budget for the labeling, then what people actually do is like they get an initial small set of labeling done. Let's say if you have 1 million data set, they get labeling done for some 5,000 or 10,000 samples, and then they run the ML model. They train the ML model and run it over all the examples, and they also try to get a confidence score. So if they have a less confidence, they consider it as a query. So what they will do is, for the output which has more confidence, let's say greater than 70 or greater than 80, they leave the labeling. For the output which has less confidence, less than 70, they try to label, they send it to human labeling and try to label it again, retrain the model, and then repeat this iterative process until their budgets are exhausted or the ML achieves comparable good accuracy which they are looking for. So the probability checking is what they mean by query, but the ML model doesn't directly query humans. And class imbalance. This is the interesting part. The three pillars of handling class imbalance: evaluation level, the prerequisite. Uh, Whenever you train an ML model on something, you cannot check the accuracy as a metric, okay? Because let's say your complete training data set is 1k example, 1000 examples, and 900 examples were some example related to one class and 100 examples were related to another class. Then what happens is, even if the model predicts uh, everything as the majority class, it achieves 90% accuracy, right? So you should not always depend on, you should never depend on accuracy first. You should check precision, recall, and F1 score to see the true performance on the rare class. Data level handling. So to fix the dataset distribution before training begins, like using undersampling from let's say either reducing the 900 examples to the level of lower or minor number class, or either increasing the minor number class to the majority class number, like increasing the 100 count to 1000 count, like how we did in the sign language interpretation example. Algorithm level handling. So this is also an interesting part, okay? So what usually people do is they try to force the model to pay attention to the rare class. Let's say if you have an exam in the training set, there were two classes. One class is uh, if the total training set is 1000 examples, and one class contributes to 900 example and another class contributes to 100 examples, so then we'll apply some weight to the cost function. Like for example, in neural network, they have this back propagation rate. Back propagation is nothing but whenever it does a mistake, it goes back and updates its weight to correct that. In that back propagation, whenever it does a mistake on the rare class, the penalty it gets is higher than its mistake on majority class. So we can implement this. You don't have to worry about this. You can easily implement this by passing a parameter in famous or good libraries like PyTorch or sklearn. You can just pass a parameter and they will take care of everything. Data augmentation, techniques for enhancing training data. Data augmentation is nothing. You have a smaller set of data and you want to increase your data set size. Then you will use data augmentation to artificially increase the data size. Like simple transformations in computer vision, let's say you have a cat image, you'll rotate it, increase brightness, decrease brightness, or you try to flip the image, change background, similar like this. And if it is NLP, you try to change a word with a synonym of that word to have a new sentence, a new completely different sentence. Perturbation, it is like adding a random noise to the existing example, like making an example blur, etc., so that it injects. If you inject some noise, it trains the model for stronger and more resilient decision boundaries. Data synthesis is, you can artificially synthesize the data. For example, look at this. There is a dog picture, there is a cat picture, and they use these both pictures, and then they just change the cat's background with the dog's background. They are not creating a new image, they are just interchanging the background, and similarly they'll do some things and get a new data point. If it is NLP, they'll just use a template like find me a cousin restaurant within number miles. Your cousin and restaurant were like, you can interchange the values here with different cousins and numbers, so that you'll have hundreds of examples getting ready in few minutes. And nowadays you can use this generative models, LLMs, to get this data synthesis very easy. If you apply these techniques, proper sampling, labeling, and algorithm level balancing, you won't just be building models, you will be engineering robust ML systems that actually survive in production. I'm currently building a lot of these concepts from the ground up, and I'll be sharing those right here on this channel. If you want to learn how to build genuinely good AI products, hit subscribe, drop a comment below if you have any questions, and I'll see you in the next one. Thank you.